Hello and welcome back to Part 9 of the Delaware Tech Physics 111 Exam 1 Preparation and Practice Exam covering motion, also known as kinematics. In this section, we're going to continue with horizontal kinematics problems. The last time we did simplified horizontal problems that just used the standard speed equation, but now we're actually going to be using the 5 kinematic equations. And this is a problem with horizontal motion. It says a car starts at 30 meters per second, so that's plus 30 meters per second, and slows down to 15 meters per second in 25 seconds. So we know several things. We see 3 numbers in here, and we're asked to draw a diagram of the situation. And you can use the table of givens first, or you can do the diagram first. It doesn't really matter. They will both have the exact same information in them. So let's start by drawing our diagram here, and it doesn't have to be pretty. There's my car. It doesn't have to look like a real car. And we have a car in the beginning. That's our initial. That's our final car. And the car is going from one location to another. It starts out with a initial velocity of 30 meters per second, technically plus 30 meters per second. And our final velocity is also given. It says that it is 15 meters per second. That is positive 15 meters per second. And this whole transformation takes a total of 25 seconds. So that's our change in time. That's our time that this whole thing takes place. And we need to complete our table of givens. And you should remember the one box should be your displacement. This is horizontal displacement, so use delta x. We have 2 velocities, our initial and our final. And since the 2 velocities are different, that means there must have been an acceleration that took a certain amount of time. And there are 5. So now we just fill in the information we already know. Plus 30 meters per second is our initial velocity, plus 15 meters per second is our final velocity, and 25 seconds is our total time. That is, it's our change in time. We don't know the acceleration, and we don't know the displacement. So at this point, we can scroll down, keeping our table visible, and we're asked, what is the acceleration? So that means we have 3 pieces of information here. The 2 velocities, the change in time, and we're asked for an acceleration. So we want the one formula of the kinematics set of 5 formulas that has these 4 variables in it. We don't need one that has displacement in it because we don't know displacement and we're not asked for displacement. So we're only looking at these 4 items, and the only equation that has those 4 items in it is equation number 2. It is the one that says the final velocity equals the initial velocity plus the acceleration times the change in time. All right, so we see our 4 variables. Here is the one we need to solve for. We always write the equation without numbers in it first, then we write in our numbers. We have plus 15 meters per second is our final velocity. The use of the table is to make sure that the numbers you're putting in the formula match the numbers in your table. So make sure your table is correct based on the question. So our final velocity equals our initial. Our initial velocity is plus 30 meters per second. And that's plus a second term, which is our unknown acceleration, times our known time, which is 25 seconds. Now, for those of you who struggle with algebra, The idea here is we're solving for A, so we want to move everything that is not A away from A to the other side of the equation. And we start by moving the things furthest from A over to the other side. Well, this is the thing that is furthest from A right now. We move that first. It's being added to A, so we need to subtract it from A, from both sides of the equation. So if we subtract 30 meters per second from both, that term disappears, and now we have that A times 25 seconds equals this sum. So it's positive 15 meters per second and minus negative 30 meters per second. We add those together, we get negative 15 meters per second. We divide both sides by 25 seconds to get rid of that term. That cancels, and now we have that acceleration is equal to this term here. So we take our calculator, we divide negative 15 by 25, and we get a negative number, negative 0.60 meters per second. You'll notice it's meters per second, so it's meters per second squared, which is an acceleration unit, and that is our answer. So let's scroll down to see the remainder, same problem. The last part of this problem says how far does it move during that time? Okay, how far does it move? You're being asked for a distance or a displacement. You're not asked for a time, you're not asked for a velocity or an acceleration. You're asked for how far it moves, and that's the remaining variable we haven't calculated. We know the other four variable answers. We know those values. We just don't know the displacement. So what we need to do is scroll back up to our formulas and decide what formula we're going to use. Well, we've used formula number 2, so we can't use formula number 2. And besides, it doesn't have displacement in it. The other 4 formulas all do. So it's up to you to pick the formula you want to use, the one that's easiest for you to use. Most students pick number 1, some students pick number 3. So let's use number 1 for now and see what we get for our displacement. So our formula for displacement, the formula number 1, is the displacement is equal to 1/2 times the sum of the two velocities, which we both know, times the change in time, which we also know. We plug these in, 1/2 times our two velocities. We have positive 30 meters per second for our initial velocity, and we have positive 15 meters per second for our final velocity. And then we multiply that by our time, which we know also it's 25 seconds. If you want, you can add these two together now and realize that's 45 meters per second, technically plus 45 or positive 45 meters per second. And now we have our new equation. Oops, let's get that out. And our new equation, we'll just write it a little bit lower here, is 1/2 times 45 meters per second, that's positive 45 meters per second, times 25 seconds. Plug that into a calculator, and you would get 562.5 meters. Now, what did we forget? This is a displacement. It's a vector, so we have to have a positive sign in front of it, negative if it was going to the left. So that is our answer for that problem. Now we can stop here, or we can check our work. Remember, I said we could have used formulas 3, 4, or 5 as well, and 3 is pretty straightforward. So let's see what happens when we use formula 3 instead. So formula 3 says that the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Remember, displacement is what we're trying to solve for. We know the final velocity is plus 15 meters per second, and we need to square that. We know the initial velocity is plus 30 meters per squared, meters per second, quantity squared. And then we have 2 times our acceleration, which we now know is negative 0.6. Get rid of that. We can. 0.6 meters per second squared. And then we don't know our displacement here. Well, we know with a calculator 15 squared is 225. And we're squaring meters per second. That means we have to square the meters and we have to square the seconds. 30 squared is 900. And that's also meters squared per second squared. And we've got these two terms. We might as well multiply those together. 2 times negative 0.6 is negative 1.2. And we only have one set of units, and that's meters per second squared times our unknown. Well, we need to move this term over to the other side. We subtract it from both sides. And when we do that, we get a total on the left. Remember, this is 225 minus 900, and that would be equal to 675 meters squared per second squared, and that's a negative number because we're subtracting 900. And that is equal to negative 1.2 meters per second squared times our unknown. So our unknown, delta x, I'll write it over here on the side, is equal to this number divided by this number. That's negative 675 meters squared per second squared over negative 1.2 meters per second squared. And we're dividing units as well as numbers. When we divide these, you'll see that the top number, the numerator, has one more meter in it than the bottom, so our answer is going to be in meters. The negative signs cancel. When we divide this out, we get exactly the same answer we got before. We get 562.5 meters, and that's a positive number. It's the same answer, so we can be pretty confident that we did our problem correctly. Okay, so let's take a look at our next problem. Now, on your exam, you're not going to get your problems in order where all your horizontal problems are grouped together, all your vertical problems are grouped together. Things might be mixed up, so you have to read every question carefully. But this is another example of a horizontal kinematics problem. So in this question, you're told that a car is traveling at 24 meters per second. That's plus 24 meters per second, positive 24 meters per second. And it slows to a stop with an acceleration of negative 3.2 meters per second squared. Well, you see two numbers in there. That's great. But where's your third number? Well, you have to read the question carefully. A car driving at 24 meters per second, well, that's our initial velocity. Positive 24 meters per second is our initial velocity. It slows to a stop. That's our final velocity. Our final velocity is 0 meters per second. And then we have an acceleration. So we have our three numbers. This is a problem with acceleration that is not 0, so we have to use our kinematic equations, the set of 5 equations. So let's draw our diagram. It says draw a diagram of the situation, before and after diagram. On an exam, it's not going to say before and after. You have to know, draw before and after. So let's consider our before, our very simplified car before. our very simplified car after, something happens in the middle, and it comes to a stop. We know our initial velocity is positive 24 meters per second, and we know since it comes to a stop, our final velocity is 0 meters per second. And then, of course, our third number is right in the problem. It says that what happened was there was an acceleration, a negative acceleration. In everyday English, we would say deceleration, but to a physicist, any change in velocity, making it faster, making it slower, changing direction, all three of those are changes in velocity, and therefore all three of those are examples of acceleration. So here's our acceleration. We fill in our table. This is a horizontal problem, so we use horizontal displacement, delta x. We have an initial, we have a final velocity, we have an acceleration, and we have a certain amount of time it takes. We know the initial is plus 24 meters per second. We know our final is 0 meters per second, and we know our acceleration is negative 3.2 meters per second squared. Remember, that's our unit for acceleration, plus or minus meters per second squared. Now, we scroll up a little further and we see what the problem is. It says, how far did the car drive before it came to a stop? How far did it drive? Well, that's asking for a distance. Technically, it's asking for a displacement. We want a delta x, okay? A change in x, a change in position, displacement. So we have to find a formula that has these three parameters in it, as well as our delta x. So we don't care about time for now. So we look for a formula that's missing time. Well, we go back up to the formulas, and the one that's missing time is formula number 3. Final velocity squared equals initial velocity squared plus 2 times acceleration times the change in position, also known as the displacement. So we scroll back down and we write our equation number 3. So equation number 3, VF squared, sorry about that, equals VI squared plus 2 times A times our displacement. Remember, we're solving for displacement. We have the numbers. Scroll down so we can see those numbers. And we start plugging them in. Our final velocity is 0. Well, that makes squaring that value easy. 0 squared is 0. And that's going to be equal to positive 24 meters per second quantity squared. Remember, you're squaring the number and you're squaring the units, plus 2 times the acceleration, which is a negative number. Don't forget the negative sign, times our unknown displacement. Since we're solving for displacement, we want to move all the terms that are not displacement over to the left. And you want to start with the terms that are farthest from it. Well, let's first figure out what 24 squared is. We plug that into a calculator. We get 576, technically positive 576, meters squared over second squared. And those of you worried about the units, don't worry about the units. If you do the math properly and you're calculating a displacement, it should be in meters, plus or minus meters. If you're doing a velocity calculation, it should be in meters per second, plus or minus meters per second. If you're doing an acceleration calculation, it should be in meters per second squared, technically positive negative meters per second squared. And if you're calculating time, it should be in seconds. So as long as you remember what your final solution is, what you're solving for, that will tell you what the units are. All right, so we're going to be moving this to the other side, which this is this. So we have to get rid of it. So we subtract 576 from both sides. And I'm not going to write the units for now. And we subtract this out. Now we have negative 576 meters squared per second squared equals this term times this term. Well, let's just multiply this out. This is 2 times negative 3.2. Well, that's negative 6.4 meters per second squared. So we have this is equal to negative 6.4 meters per second squared times delta x. And if you're stuck with the algebra, go to a math instructor or go to a physics instructor. We're happy to help you out. Since now the only term that's with the delta x we want to move away is this term, we divide, it's multiplying times delta x, so we divide both sides by that number, negative 6.4 meters per second squared on both sides, negative 6.4 meters per second squared, and we get that delta x equals 90, positive 90. So this is in meters, and it has to have a positive or negative sign. It's positive because the negative and negative cancel each other out, and we get a positive 90 meters as our displacement. And if you want, you can write that up here just to remind yourself you calculated the 90 meters as your displacement. Now scrolling down, we see that the problem now asks for how long did it take the car to stop. It's asking you not for a distance, but for a time. This is saying how long did it take. It is a time period. And you have your choice here of determining whether you want to use formula 1, 2, 4, or 5. Remember, you just used formula 3. You can't use formula 3, so you can use anything but formula 3. So we want to solve for time. We scroll back up to our formulas. You can use your formula sheet to do this and decide which formula will be easiest to solve for delta t. Formula 1 looks pretty easy. Formula 2 looks pretty easy. And you could use 4 or 5, but I think most students would pick either Formula 1 or Formula 2. Let's try Formula 1 first and see what we get. So Formula 1 states that our displacement, which we know is positive 90 meters, we just calculated that, equals 1/2 VI plus VF times our change in time. And time is the thing we don't know. We know that the displacement is positive 90 meters. 1/2 is 1/2. That's easy enough. Our initial velocity is positive 24 meters per second. And our final velocity is just 0 meters per second. So that makes that math easy. And then delta t. These, when we add them up, obviously add up to 24 meters per second. So now we have 90 meters, I'll leave out the positive signs for now, equals 1/2 times 24 meters per second times delta t. We multiply 1/2 times 24, we get 12 meters per second. And we want to move this term, the 12 meters per second, to get rid of it. So we divide both sides by 12 meters per second. We divide that by 12 meters per second, and dividing this just cancels that term. And now we're left with delta t equals 90 meters, positive 90 meters over positive 12 meters per second. If I can get this to write properly. And that gives us a delta t of 7.5 seconds. That's our answer. Now, if you want to be sure you have the right answer, let's give ourselves a little room and we'll use the other equation. We just used equation 1. Let's try equation 2. Equation 2 says that the final velocity equals the initial velocity plus this other term with the acceleration times delta t. We don't know delta t, but we know everything else in this formula. Our final velocity is 0. That's easy enough. Our initial velocity is plus 24 meters per second. And then we have another term. We have acceleration, which we know is negative 3.2 meters per second squared. That was in the problem. And then that's times delta t that we don't know. We need to move the term that's farthest from the delta t to the other side. That means we have to subtract that term out from both sides. That cancels this. And now we have negative 24 meters per second equals negative 3.2 meters per second squared times delta t. We divide both sides by 3.2, negative 3.2 meters per second squared. Get rid of that term on the right side. That'll cancel that. And now we have this. Of course, the negative signs cancel. If you do it with a calculator, it won't matter. And you divide that out, and we get delta t equals this divided by this, and lo and behold, we get the same exact 7.5 seconds, and we know that we've done it right if we get that. And we'll stop here.